I'll just share what I did. Yeah, I just did this before Maghrib. So what so what I did, I remember that I mentioned to you the can you see this?
Okay, yes, I can see your.
So so if I run this, yeah. So if I run this, um, what I added last time is that the problem was the problem at that time was that this pump it's connected to the compressor downstream, and then they are a bit like a pressure balance here. So if there is no flow here because the pressure of the compressor is maybe too high, and then the pump will then stand still, and then it creates that sometimes it creates back pressure, and then sometimes it just doesn't work. And then also the thing we forgot when we did this pump, we forgot to specify the duty, so it was 0. So in this case, what I did is just I added the like a minimum line, so to say, back to the vessel. So in case that we don't have like enough pressure or not enough flow rate going through this line, that pump can always be running in its minimum line, for example. Yeah, so in this minimum line, or how I did that is just like a very simple, make a very small CV of the valve, because it's basically it's an orifice, or it's a very small control valve, and then make a small valve opening. So it's in that sense it creates this minimum flow about 7 to 8, and then the actual flow here is in 145 or something, that is going flowing through the to this main product. So that's the only thing that I changed, and then we can see now it's running smoothly. Yeah. So I think yeah, by this point, then I think you understand what it takes to do the dynamic simulation, right? So just to recap, yeah, in dynamic simulation, it's better for us to use pressure flow solver. So the flow is then defined by the pressure balance, and then all the streams coming in and out, we have to add like a valve. Yeah, we have to add a valve to be on the safe side. Like in this case, the feed is then added by the valve, and then the outlet, there's only one or two outlets, and then they are also with the valve, and then yeah, and then we are good to go. Just specify the pressure in, and then specify the pressure out, and then all of the equipments in between, they have to be sized adequately, so that we can run it. And then it's also like I think we see already now, if we don't have, like, for example, appropriate control schemes in the system that we are going to simulate. Yeah, if we don't have an appropriate control schemes on the system that we are going to simulate, well, the system itself is not going to run well. Yeah, so we see problems here and there, and then I saw last time we saw that this pressure is too high, so it goes back to shooting up the pump, which I found this before Maghrib, and then hence I increase the pressure here, and then make a check valve over here. So check valve to prevent backflow, which indeed in real life we have check valve downstream of the pump. Yeah, in practice as well, we use process dynamic to evaluate whether our control stream to evaluate whether our control scheme is correct or not. Yeah, so that's also the use of this process dynamic. So I think I will so far, do you have any questions on this exercise?
No, it was good. It was clear.
Yeah. So stop, and then Because last time you asked me to do so that we can discuss
how to design PSV.
a PSV. So that how to design a PSV is it's not part of a HYSYS. Yeah, I mean the HYSYS can help you to do so, but then I think, do you know this book? You have to read. You have to read standard API 521. I think if you know this book, because at UTP as well, if you took, I don't know what you took for your election, yeah. If you took process safety, that means you had also a higher chance to meet me at that time. So we use this book, Chemical Process Safety, and then in the chapter. So this book is like a more like a short compilation of the standards and then booklets and then all informations on the chemical Center of Chemical Process Safety (CCPS) of the United States. So in chapter in chapter 8, you will learn about the types of reliefs, the locations of reliefs, and then on chapter 9 is then the sizing. So the PSV valve itself, it's typically either conventional spring loaded or balanced bellow. We will see that later on. And then it has the example on liquid service or vapor and gas, and also like a two-phase flow. Yeah, so we have the PSVs for liquids and vapor, and then we have ruptured disc for liquid and vapor, and it's also like a two-phase flow. So we will see, I think we will see the calculation itself is straightforward. Yeah, it's page 384. 384. 384. So basically, you know orifice, right? I mean valve, right? So if we have I think I need to go before I. Do you know how this work, right? I mean this PSV. So for example, just take this one. So you have so now to check your understanding. So this one which it says that what's wrong. So in scheme F, what is wrong here? So what is wrong is that typically, because we have a higher pressure here in this vessel, right? So we have a higher pressure, and then it's being released through the orifice of the PSV, and then hence, because it is then being expanded through the PSV, that means this part from this point on downstream, yeah, from this point on downstream, it has a lower pressure here. This is then the lower pressure area. This is the higher pressure area. Because it has a lower pressure area, that means the density is going to be low. If the density is going to be low, that means for the same mass flow rate that we have to release, the volumetric flow rate is going to be very high, or it's going to be larger. So in that sense, to accommodate for that larger volumetric flow rate, we have to size this pipe larger than the inlet. Yeah, it has to be larger than the inlet. Hence, we will see that the flow is then going to be very smooth. So so if this then if the operating pressure is about 5 bar, and then you have incoming like 10 bars, so that 10 minus 5 bar is the one that we have to release through this PSV. Yeah. So so in that sense, we have to know what the set point is, yeah, for the set point is, and then we need to know the pressure here, the maximum that it can handle, which is then the set pressure, the set point or set pressure, and then the pressure downstream, yeah, pressure downstream, because the amount that we can release the amount that you can release is then depending on the pressure here and then the pressure there. So the difference between them is then the amount that we can release instantaneously. Yeah. So in this is in the book. So it's the calculation itself is very straightforward. If you see this, there's a percent over pressure. I think you can imagine, yeah. So if we increase the overpressure, means 0 means it's 100% like a design pressure or maximum operating pressure, for example, yeah. So this then 0 is then your maximum operating pressure. So if you let the pressure increase by 10% of the maximum operating pressure, and then your corresponding vent area, the orifice of the PSV is going to be lower than if you release it at exactly at the how do you call it, exactly at the maximum operating pressure. Yeah, it's simply because you have a higher delta P. That's number one, and then yeah, that's basically it. Yeah, so we increase instead of from 0 to like 1 atmospheric. Yeah, from the, I don't know what is 0, maybe 0 is then 10 minus 1 atmospheric is 9, compared to like 10.1 to minus atmospheric. So we have a decrease in the size of the PSV basically. To know yeah, okay, one more thing, editor, to know what is then the how to size this, to know how to size this, is that we need to do like a quick calculation on how much we are going to release. Yeah, how much we are going to release. How much we are going to release really depends on the scenarios that we are thinking that we can find in the process. For example, I think this one, this one, yeah, I just take any. So in this case, we can have a PSV in these two vessels, PSV in the coolers, and then PSV in the and this what else? Yeah, in this line, for example, this line, this displacement pump. So for all of these PSV, for example, just take the PSV over here that we are going to make. So we need to specify the scenario. What makes the PSV? What makes then this vessel goes over pressure? Yeah, because then that's the use of the PSV, to release that overpressure. So we could say that this line is then stuck close, and then maybe this valve, or this valve is then fully open, or maybe there's a runaway reactions, or maybe there's a high pressure, and then this is then fully opened, and then that anything that could create the overpressure in the vessel. So in this 1, 2, and then 3 scenarios, we need to be able to calculate how much is then the release load. So based on that release load, and then the set pressure, and then the release pressure, the downstream pressure, we can then calculate how much is in how big the size of the PSV. So to go quickly, so basically this is then the equations, yeah, for the liquid release, and then they have the let me see, okay, yeah. So it has this then the area, and then all of the units, and then QV is then the volumetric flow rate through the relief in gallons per minute, and then CO is then discharge coefficients. It's typically, we could take like 0.6 or 0.7. If we have the vendor data, and then we could use the actual vendor data. If not, it's a 0.6 and 0.7 is good enough. KV is then the viscosity corrections. Yeah. So if we have like because what they did, we need to go to this API 520 to know what kind of liquid that they use to develop this equation. It could be water, I don't know. So so it says here many process fluids have high viscosities. So to account for these high viscosities, that means we need to add these corrections. KV is viscosity corrections. KP is then the overpressure corrections. Yeah. KB is then the back pressure corrections, because back pressure means the pressure downstream. And then square root of the specific gravity, specific density, and then the PS is then the set pressure, and then PB is then the back pressure. So that we need to know the flow rate, we need to know the set pressure, we need to know the back pressure, and then the properties of the fluid, and then we can just key in all of the constants, and then we can get the A. So that's basically how it's very easy basically how to use this. So we have all of these KV corrections. So yeah, so if we have a different Reynolds number, and then we can see what is then the correction factor of our KV. If we don't know, for simplicity we can just put 1 KP as well over pressure. So if it's like a 10%, it's 0.6, 15% it's higher, and so on and so forth. This is then the KB corrections, so depending on the back pressure and the set pressure ratio. Yeah, so we'll see for example, yeah, 200 gallon per minute of water, it's pumped via positive displacement pump, and then the pressure discharge is then 200 psig. And then because a dead-headed pump can be easily damaged, there is a relief valve. Let me draw this so that you understand. So basically we have a pump. It's pump, and then this positive displacement pump, and then we have a valve, and then we have a relief valve here, basically. So this pump is then delivering the flow rate of 200 gallon per minute, and then 200 psig as well. Yeah, at this point. And then somehow this valve is then closed. Yeah, some guy kicked the valve and then it's closed or whatnot. So this one is closed. So because this is closed, and then the pump is then keep on running, yeah, keep on running, and then this is then the positive displacement pump. So it will then create the pressure in this line. Yeah, it will create the pressure in this line in such a way that the created pressure can exceed the design pressure of the line itself. And then if the pressure exceeds the design pressure of the line, it will then be explode or whatnot. Yeah. So to prevent that from happening, we install what they call like a pressure relief valve in this case. So assuming back pressure of 20 psig, so that means this pressure here, PB, is then 20 psig. Yeah, and then overpressure, we have two cases, overpressure of 10%. So 10%, so this part here, PS is then 10% of 10% times 1 times the operating pressure. Am I right? No, I'm not right. So I have to remove this. So the set pressure is then, in one case, is then 1 plus 10% times the operating pressure. Yeah. So so it says here, so we can just go through here. The set pressure is 200 psig. So 200 psig is then the pressure, and then the back pressure is 20 psig, and then the overpressure is 10% of the set pressure. So we'll take 10% over here. And then the C naught is then we just put 0.6, and then the amount that we want to relieve, yeah, because it keeps on pumping, so 200 gallon per minute, so we need to release the same amount of liquid. And then viscosity correction is then just take 1, yeah, because it's high flow rate, and then it seems to be like a very turbulence. And then the KP because it says the 10%, yeah, so we need to go to figure number 93, this one. So 10% is 0.6 basically. So we have the KP 0.6, and then the back pressure is not required because this is not a balanced bellow spring relief, yeah. It's just a spring loaded. What is balanced bellow, what is spring loaded, maybe we can discuss it next time. um, or you can just Google it yourself, yeah. So KB is then 1, so it's just a matter of plugging in. So we have KV 200, put 200, and then CO is then 0.6, KV is 1, KP is 0.6, KB is 1, and then because it's a water, yeah, it's a 1 as well, and then 1.25 PS is then the set pressure here, 200 psig, and then PB is then this guy, the 20 psig. Now it says here the PS is the set pressure, so it seems to me that what they use as PS, this is then the PS, and then they're not using this as their set pressure. So basically it's they take this number, not in these equations, so they take this number to for the KP graph. So that's where they account for the for that 10 pressure over here, yeah. And just plugging in, and then they get this diameter area, sorry, the area of the orifice, and then they get diameter. So we get now the size, we know then the size of the PSV. And then I think we can Google this, what is then the corresponding type of the PSV. Nah, we can just take one. I don't know. We saw that the it's a 1.1 inch, right? So the diameter. Where's that thing again? So 1.1 inch. 1.1 inch is somewhere here between the H and then J. So in our case, typically we will then select the next highest higher PSV. So we will select PSV of the size of J, yeah. So 1.2. So that's basically how we size it manually. The same goes with the if we do in vapor. We have additional computations, so we need to know whether the flow is choked or not choked, yeah. So if the flow is then choked, then it is then the equations that we have to use. And then this then the area, the equations that we have to use. And then if it is this is choked, yeah, and then blah 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 blah. And then if it's not you can have this you can just go through this. And then if it's not choked, not choke, and then we can just use equation 448, yeah. So it's in chapter 4, not in this chapter 9, but it's 448. So 448 is somewhere. this. So if the flow rate is not choke, that means we can just use this mass flow rate, and this then the area that we have to calculate. Yeah, so we do the math and then we get the area. And then to know whether it's going to be choke or not choke, that means we need to find out what is that the choke pressure. Okay. So if and this is how we calculate the choke pressure. So if the pressure downstream is less than the choke pressure, that means it's a choke flow. If not, then it's we can just use these equations. So that's basically what this is. And let's see how we can do the same calculation in HYSYS. Yeah, I haven't done this myself basically. So let's just go through this together. So we will do liquid and then we will do vapor, because we have the examples and the solutions basically. Yeah, so we will use this, and then the okay, I tried something, but I'll just redo this. I'll just make another one. So far, do you have any questions? Yeah, I know that I went through this very fast, because the question was to how to use Aspen HYSYS to do the calculations, which I respond. You don't need to use Aspen HYSYS to do calculations. You have to do the calculations like either in manually. Yeah, Aspen HYSYS is just like yeah, I mean it's just like a tool. Purging come from PSV. What do you mean by purging? Because if we purge and then what we call purge, if I understand you correctly, we call it blow down. So blow down is just typical valve. Yeah, purging is the PSV is pressure safety valve. So it's anything that if you want to have instantaneous release. Yeah, blow down is a control release. Okay. So we'll have like let's see, we have water and nitrogen, for example, because the air is nitrogen. Simple case, so just you like an ideal thermodynamic. Oh, okay. Any other questions? Oh, why do you mute Safik? I don't know. So okay. So we will do. Think we can go straight to the safety analysis. Can we do so? I'm not really sure. Add PSV. No. Okay, that means we need to do something else, yeah. So we need to if it's stream, then we need to get we need to get the stream. How much was that? 200 gallon per minute, 200 psig. Compositions water. Uh, 200 gallon per minute. Gallon. US gallon. Yeah, okay. We just use US gallon. So it's also UK gallon. I didn't know all this guy thinking. So 200, right? 200. This is 200 gallon per minute. 200 psig. 25 degrees C. In this case, can we go straight away? Nah, and then we add in, I don't know. Yeah, okay. So we can just I add click PSV and then just tap to it, so it has this guy, and then double click. Yeah, create emergency scenario. Operating temperature reference design temperature. Yeah, make 50. Operating pressure 13.78 bar gauge, and then what we had is 14.8 bar absolute. Yeah, 13.8 bar gauge, and then the design pressure as well, 13.28 bar gauge. Scenario. Yeah, I don't think we need to create the scenario. We can create scenario. User defined. Yeah, the scenario is that in the standards, in the API standard, there are several scenarios that we have to consider. So the use of this scenario is then so that we can generate or we can calculate the release load. Yeah, the release load. So that's basically what the use of the scenario is. But in our case, we know that our scenario is then we need to release this 200 gallon per minute. So that's our scenario. So we get already the flow rate. So let's see, liquid flow rate empty, sizing case. Yeah, let's see. This one. So what I did is then just double click on this PSV, double click on the scenario. Just rename this scenario. Yeah, so rename this scenario is then the pump blocked. I think we have the scenario here somewhere. Blocked outlet, fire, blocked outlets. Yeah, okay, blocked outlets. Double click. And then we have the relieving temperature of 25 degrees here. It's the same relief temperature. Relief pressure is it's 200 psig. 200. Can I not do this? It automatically reference stream. Oh wait, no. Well, let's just use this. Yeah. I don't know how to edit this. And so 200. No, I cannot do so. So the back pressure, it says back pressure is, just follow this for a second. Yeah, we know that we're going to have a smaller size. Back pressure 20 psig, 20 psig, psi pressure, build up back pressure, sorry. Yeah, 20 bar, 20 psi. Okay, 20 psi G. Yeah, okay, it's G. It's all absolute basically. 20 because 15, about 15, 14.5 is then the 1 bar absolute, so 20 is then higher than 1. Nonetheless, calculated back pressure factor, yeah, let it calculated, and then click OK. Liquid, and then relieving flow is 200 gallon per minute. Yeah. That means we have to do some math, but I don't like doing math now. We can just ask this guy, unit converter. Come on. 200 gallons. 200 gallons. Gallons US. It's in liter because it's water. Yeah, we know water is then 1 kilogram is 1 liter roughly. So in this case 200 is then 757 liters, which means 757 kilograms as well. So we go back here, 757 kilograms an hour. Yeah, it's a we have 200 gallon per minute. That means 757 divided by 60. How much is that? Calculator. Come on, why is it so slow? 12.6, thank you. So 12.6 kilogram an hour. Okay. So it says calculated orifice is this one. So it's 1.81 centimeters square. How much is that in inch square? Oh, yo. So so the D, we need to have the D, 1.1 inch, and this one, centimeter square to inch square. Where's my thingy? Inch square, centimeter square to inch square inches. Okay, so now 0.001181 0.00, yeah, 1 point. Okay, so it's supposed to be like very small one, and then this small one is then square inch, and then if we calculate the diameter, how much is that? That one I don't know, but we know that it's going to be small, because we have a higher relieving pressure here, which I don't know how to edit. How to edit this? yeah, how to edit the okay. So operating pressure, for example, is 200 psig, right? 200 psig. 200 psig. 200 psig, and then design pressure as well, 200 psig. Yeah, and then can we go back to scenario? Allowable. Now how to change this? Yeah, equipment. Let's put this. If it's 200 psig, it goes by 2 bar. It goes by. It's very strange. The daytime and type pressure. Is that really? Is that correct? 13.78 times 1.1. 1.7, yeah. Okay. Okay, in this case, okay, yeah. But in our case, for example, okay, yeah, you're right. So in our case, we have the release pressure at 200 psig, the same release pressure. So in our case, that means we have to make this into 0. So it's the same. And then back pressure is build up back pressure 20 psig, 20 psi. Yeah, I think this is it. 20 psi. Let me think. And then this is 1.245. It's a 0.00000193. Seems very small. It's because it's 0.9. Let's see what we did wrong. What did we do wrong? 12.6 kilogram an hour. It seems to be correct. In 200 gallons, 757 liters. Oh, okay, sorry. We have 200 gallons per minute, so that means this 757 liters per minute. 757 liters per minute. That is why 757 liters per minute and 757 kilogram per minute. Kilogram per minute, and then divided by, yalah, betul lah, 757 12.6, ya, betul kan? This one is yeah, we have not divided by multiplied. Come on now. No. 757, that's in minutes. And then if it's an hour, that means we have to multiply it by 60. 45, 520. Okay, thank you. 45, 45, 520. Klik apa nama? Yeah. Now we'll see. This is 3.9. Area. 3.91. 0.6 square inch. So it's not quite right. So 0.6, it's now 0.9. Something is missing somewhere. Yeah, something is missing somewhere. So what we don't have in the HYSYS that we know that we have the CO. Yeah, 0.6. 0.6. Yeah, and then the now it's 4.167, and then the what else? Yeah, 4.167. So it's a 0.64 now, but I'm missing still the KV is one, KP and KB. I think KB is also one. KP, KP and KB. Pressure, leaving pressure. It's the same. Calculated back pressure calculated. We put one. Back pressure KB, then the back pressure vector is it's a 1. If it's calculated, it has to be 0.6. Let's see what happens. For conventional opal operated type valve, KW should be 1. Yeah. In this case, it's a 6.9. 6.9. This one. 6.9. Yeah, it's a 1 something. So it's somewhere around. It's now bigger than this guy. 0.8, 8.9. So there must be somewhere this back pressure calculation, because we have everything I think set. Yeah, flow rate is okay. This one I don't know. This one, hopefully if they're using the same equations as in standard, they will use this 0.6. This one we don't know. If it says the spring loaded, it has to be 1, but in this case we are using this to be 0.6. 10%. Let's see which one is 10%, Aisha. This is 10%.
At relief pressure.
Relief pressure.
13.79. Let's just try. I don't know.
Let's try, yeah. Because it will then relieve it at a higher pressure. Nonetheless, let's see, yeah. At 6.592. 6.592. Yeah, I still won. So what's better ways is then we go to this documentation builder. Oh, this relief load calculation. No, the sizing. we'll see what the equation is. Yeah, we add, yeah, okay, we just add that. Let's see what the equation is here. Liquid. Oh, ini. See the same number, same equation. We have 38, Q, KD, KW. KD is then the coefficient, the 0.6, yeah, the 0.61. By default it shows us that it's a 0.65, and then we change it already to 0.61, and then KW is then the what's that KW? I don't know, it's not shown what this KW is. Nonetheless, KC is then the correction factor. Oh, default 1. Okay, we did 1 because we don't change anything. And then KV is then the viscosity correction factor, so it has this, so it is calculated automatically. Hopefully this KV, because it calculates the Reynolds number, yeah. This Reynolds number depends on the size, because it's rho VD over mu, so that D is then the diameter, and we don't know which diameter that it takes into account here. It has here this one, REQ, we have Q, and then GL is then gravity, viscosity, and then A. See, A is then calculated orifice size, so it calculates the I think it calculates the orifice, this orifice, yeah. So it calculates that one, hence it gives this iterative calculations of the KV. So nonetheless, it has to be like more or less okay. But it's just that I have this concern that KW should be 0. That is basically the KW should be 0. I think that's the same statement as in this case. KB. KW is then KB, back pressure corrections, because it is not balanced below, means it is spring loaded, like in this case. If it's spring loaded, that means the KB is equals to 1. So that KW seems to be the KB. Where's that thing? The KW, so it has to be like 1. Calculated, maybe 1. But it goes back to this 3.9. 3.9, so it's very small. 0.6. But it doesn't say this one, yeah. Remember that P1 minus P2, we have the 1.25 as the
Yeah, they don't have that
this 1.25, so they don't seem to have this. So because if they have it, that means this whole thing will become this is then going to be smaller, and then the square root of the small, it's also small. Yeah, but nonetheless, okay lah. So we could do so, yeah. I think we can do let's do this. 3.9. So we can make H instead of J. Instead of J, we can use H. Select this one and then the rating. This is then the line sizing downstream and then the, upstream and then downstream. Yeah, this one we can do like a line sizing rating later on. But I'm wondering how we can add this to the simulation. It's a H, yeah. Let's do the other one, yeah. Where is that thingy? The gas. We have the example of nitrogen, I believe. So nitrogen. We have and then the composition is 70, 150, 70 Fahrenheit, 150 PSIG, PSIG, yeah, and then the so in this case we need to calculate what the flow rate is. So it calculates the flow rate, so it's 106 pound per second. 106 pound per second. 106 pound per second. Yeah. Operating pressure 150. Design pressure is also 150 PSIG. Oh, it's higher than design pressure. Make it 9. Scenarios. We have it says here the scenarios is that so we have nitrogen. I'll just draw this for you. So we have yeah, so there's a vessel, a reactor. We have nitrogen 9. This is then 70 degree F and then 150 PSIG. This is then the relief. So this is then set at 50 PSIG. Yeah, 50 PSIG. And then while this source pressure is at 150 psig. So somehow this is fail, right? So the pressure regulator here is then fail. So this valve is fully open, so it will then expose this tank, this reactor, into 150 psig continuously, right? So so it has to release at 50 psig. So basically, and then the back pressure here, PB, is then 20 psig as well. So based on the sizing of the the 6-inch diameter, they need to know, number one is then they need to know, based on this P, and then that P, they need to know whether it is choked or non-choked. It says here choke. They did already the calculations, and then if it is choked, they can calculate how much is then the flow rate that goes through from this point to the vessel, and then and then they can calculate this, so that one, and then we can go back to our this guy, relieving, I don't know, 25, relief pressure, set pressure is 10.34, right? I guess so. Baggage, pressure, psi, bar 50, 3.44. Sorry, the the this one, because what we want to size, because what we want to size is then this pressure here, the set pressure, the 50, and then the 2 bar. So this is then the conditions, not this one. So this number, this value is required to calculate how much is then the flow. So that flow is then the one that we want to release, based on these conditions, the set pressure of 50 and then the 20. So we have to do this all over again. I think I can do it directly here. Um, 50. So operating pressure is then let's make it like if the release is 50, psig, and then this is then let's check 3. So we will release at 344. Set pressure at 344, right? And then the allowable pressure is 25 or 20, I don't know. Or 10, just use 10, I guess. 10% over pressure, so just use 10% over pressure. Click OK. Back pressure is 20 psig, 20 psig. Back pressure calculated. Okay. This relieving flow rate is 16 pound per second, 106. 1 pound per second means 106 times 381,600. 381,600 pound per hour. Yeah. It's a vapor. Okay, so 445. Let's see what they have in inch. 445 in inch. Area. 445. 68, 69. Yeah, which we calculate consistently lower. So there is a consistent error that we do compared to the book here. It's about 80 square inch. It's about 70 square inch. So we're like a 10 square inch difference. So in this case, 445. We don't have any. You don't even have the size. So what we do is that we have to select here. So we have to do like this divided by this guy. It's about like maybe 3 times. So we have to select this 3 times. So there are three orifices with this size. See, customize ribbon, customize. Total orifice required. No, I was looking for option that we can just here basically we want to select more than one. This guy. Yeah, we know. Can we not select? Lower pressure 10. Sizing scenario, sizing case, yes, sizing case. It's a balance below. Smaller. Yeah, we know it's smaller, but we don't have it, so we need to have like 3. We need to have 3. And see. Oh, add spare. Add spare. And then add spare. Spare or I'm confused now. Is it spare or the in here? Okay, so you have to spare. Or if it's quite this one, I want to have 4.
What about the equalized flow?
Equalized flow. I need to have 4, right? Basically, because it calculates for us, it calculates for me 509. 167 times 4. has to be times 4, right? Ah, 167 times 3. Nah, times 4. Need to have at spare. Let's see if I'm doing this correctly, yeah. So, equalize flow. What does it mean? I don't know. In customize type of the ribbon, customize. Oh, custom orifice size. No. Yeah, we know. It doesn't do anything. But nonetheless, yeah. In practice, that you can have if it needs to be like this size, and then while we have only like in the store 167, we have to have like at least 4 of these PSV of this size to get this guy. Yeah, I think we have passed our time. I think in the you can make. I was trying to do this just before our meeting. I was trying to make this this nitrogen, and then I'll make like in this case, if we have to, let's simulate this. Let's simulate this this nitrogen stuff, and then I'll add like 3 of these, 4 of these, and then where we know the sizing, discharge coefficient 0.16, 0.61, make pressure coefficient is 1.
This is in simulation.
In simulation. So so in this case we can have this T now, yeah. So yeah, okay. So let's make like a T. There are 4 relief, and then at the beginning we have this equals to I don't know, maybe 20%. Yeah, I just put 20%, and then after some times we just leave it open 100%, and then the whole gas will then popping up here, will then entering these vessels, and then hopefully the pressure will increase, obviously, and then it will then open this valve. But for that we need to make sure that we have pressure control first for this guy, or maybe not necessary, yeah, depending on how the simulations looks like. And then we just open this instantaneously, and to see the build up of the pressure, and then to see the relief valve. If we have 1, and then we will see what the pressure is. If we have 2, and then 3 and 4, and then we can then make a graph and then make a comparison. I think let's do that as a homework, yeah, Aisha.
Yeah.
So then I'll also save it here, and then once I done the simulation here, I will also share it with you. Yeah, so let's see if we can do this in the meantime. Okay, so questions will be next week, yeah.
All right. Okay.
Okay, thank you, yeah.
All right. Thank you, Doctor.